Okay, we have a couple of concepts left to discuss in equilibria, and then we will move on after the test to two chapters that are specific to examples about solution equilibria. The next chapter out, 16, is about acids and bases and their equilibria, and then the one that follows is about solutions that have solubility issues and their equilibria. Okay. So we've already said that equilibrium is a dynamic process, that reactant and product are constantly being converted from one to the other, but the rate forward and the rates back are equal, so the concentrations don't change over time. That doesn't mean that stuff isn't moving. Now, because this is dynamic, if we were to do something to the system to tamper with it, it would spring back and try and counteract that external effect. And LeChatelier identified this and came up with a principle that said that any external influence on the equilibrium process is met with an effect that counteracts what the external force is. So any external influence on the equilibrium process is counteracted by a movement in the equilibrium position. Okay. And we'll show you a couple of different variations on this, and then we'll throw some numbers at it. And we'll look at something called a reaction quotient and determine whether a reaction is going to move to the left or to the right to re-establish the original equilibrium. So you've got a reaction that's in equilibrium, something comes in from the outside to mess with it, the equilibrium itself counteracts that and moves the equilibrium position. Purpose being, we're trying to re-establish the original equilibrium. Okay, we're going to see a couple of different things that can affect equilibrium position. And let's start with the big one, because that's the one we've been spending all of our time looking at. It's concentration. So if I have a reaction that's in equilibrium and I have some reactants making some products, and I were to do something to the flask that introduced new reactants into the flask, now because I have a products over reactants ratio that I have to deal with, my balance is out, and that will shift to counteract what I've done. Okay. It'll make sense. So I've got some A and some B, and they're going to make some C and some D. A and B are reactants, C and D are products. So once that equilibrium is established, if I were to add something to the concentration of reactants, either A or B, then I would have a situation where, under the simplest case, we say, you have too many reactants. This thing is in balance. And now you've added something to one side and the balance is off. But that balance is dynamic. It's constantly, it has the ability to constantly move. And so it just siphons something out of the reactant box and into the product box. So addition of some external concentration of A that's going to disrupt my equilibrium position. Okay. Now my K products over reactants. K is a number that is locked in. It is your equilibrium number. You've just come and stuffed a new number in here. So the actual concentrations of reactants and products that are in your flask at this point are no longer at equilibrium. They're at some number that is something else. And I'm going to have too many reactants. So the reaction moves. And it starts siphoning molecules out of the reactant side of the equilibrium and into product. I'm going to see in a minute that when you have reactions that are in equilibrium and you're doing something on an industrial scale, that can be a real pain, because by kind of definition, the reactions don't go to completion. They're somewhere in the middle. We've seen though that values of K can be very, very large. So what we want to do is, if we're doing a reaction for profit, for money, we want to push it as far as we possibly can to the product side. And so it's always like a downside to have your reactions be in equilibrium when you're trying to make a profit out of it. But it's not the end of the story, because you can do things to fool the reaction. We'll show you a couple of those in a minute. Okay, conversely, if you added external product, the equilibrium will shift to the left because you have too many products. And you will make more reactants. And that's not normally something that we want to deal with. We want our reactions as written to make more product and consume more reactant. Okay. So here's a practical application. We have a few of these. Some industrial processes are heterogeneous, and you can always play with the heterogeneous ones. Some of them are homogeneous. Where have I got? Carbon monoxide, gas. Hydrogen as a gas come together to make methane. It's a hydrocarbon. That is a fuel. So we can make fuel out of carbon monoxide and hydrogen, entirely in the gas phase. Carbon monoxide is a toxic, colorless, not particularly useful on the big scale molecule. Nice and useful in certain chemical applications for catalysis and stuff, organometallic chemistry. Hydrogen, of course, is itself flammable, explosive, but there you go, methane, that's a fuel right there. And steam. So this is a reaction that could be happening, or is happening, on an industrial scale. What I want is somebody in my factory to make the equilibrium look like this. So nature's going to set up an equilibrium position. I don't know if I've got a value of K for this reaction. Frankly, it doesn't matter. But I want my equilibrium position to be as far to the right as possible. Let's pretend that nature sets up an equilibrium for this reaction that's right in the middle. Okay? Well, what if I could do better? We're going to combine some gas with some gas and make some gas and some gas. Who remembers entropy? We're going to do more entropy in the weeks to come, but does anybody remember entropy at all? Nope. Entropy is disorder. And gases have a lot of it. And I have 4 gas molecules on the left, but only 2 gas molecules on the right. So entropically, this reaction isn't favored. Enthalpy would be the heat change. And I have no idea, because I don't have the data for this, about how much heat this reaction takes in order to go from left to right. It's possible that that reaction is exothermic and gives out heat. I don't know. I don't have that information. I want to do this. Armed only with the information that's on the board. How do I push the equilibrium to the right? It's an industrial process, and it's a gas. So this reaction is probably run hot and under pressure. Okay? And on a big scale. I've spent hundreds of millions, if not more, on building the factory and building safe, pressurizable reactors and running at high temperatures and pressures. Gas reactions. Can't do a gas reaction in a balloon at room temperature. I mean, I can, but not if I want to make any money out of it. You've got to smash the atoms into each other. Okay? Gas reaction at high temperature and high pressure how do I move the equilibrium position to the right? There are two ways I can move the equilibrium position to the right. I could add more reactants. Okay. Now, do reactants cost money? Okay. So reactants cost money. So I could add more reactant. But at some point, that's going, how much money have you got? How much money are you asking me to play with? At some point, that's going to cost me money. So what else could I do? If you're on the debate team, what's the same as add, and all it is balance. What would have the same kind of effect as adding reactants? In terms of balance.
Removing product.
Removing product. Both my products are gases. How am I going to separate them and remove them? And in fact, all my reactants are gases as well. So how am I going to open a tap and selectively remove a gas out of this container that is a reactant, a product? Here's what you do. You run this reaction hot and under pressure for half an hour. And then you cool it down. When you cool it down, the water turns into a liquid and the water drains to the bottom of the container. You open a tap and you siphon off the water. And now this equilibrium said, where did my products go? I don't have enough product. Make more product. The equilibrium is in balance between reactants and products. And when you do something to change that balance, the equilibrium position shifts to re-establish its original position. So if I could drain reactants out of my flask, if I can drain product out of my flask, the reactants are fooled into reacting more to make more product. And so I run this hot and under pressure for a while, and then I chill the container and I drain the water out. Okay, other things that are going to affect equilibrium position. Pressure. We've said before that pressure really only affects gas reactions. It has no effect on solids or liquids. Solids have very little compressibility. Liquids only have a little bit. So solids and liquids are not very compressible. I'm going to spell compressible with an I. Compressible, oh yeah, it's an I, isn't it? Not easy to compress solids or liquids, so only gases have any impact here. Okay, so I have, here's one, I have a reaction in the gas phase, and because it's in the gas phase, it's going to respond to changes in pressure. The question is, which side wins. So my value of K here, and let's do KP. We haven't done very many KPs. Product over reactant. So I've got a PCH4. I'm going to times that by the P steam divided by the PCO times the P hydrogen raised to the power of 3. If I change the pressure in this equilibrium system, do both sides of the equation feel the pressure change the same way? The textbook example, and I'm not sure that there's one, if there is one in this textbook, but the textbook example is usually NO2 and N2O4. Do I have one? No, of course it's doing ammonia and nitrogen. I said earlier on, it loves the Haber-Bosch process. Fritz Haber, founder of the Haber-Bosch process, who makes ammonia, high pressure gases, is also the father of chemical weapons. He was a Nazi. He's the guy that gave German World War I troops poison gas. He's the person that brought chemical warfare into the 20th century. And then was a Nazi in the Second World War and developed the fabulous new Nazi weapons. And somewhere between the wars, they gave him the Nobel Prize. Whatever. If I change pressure, let's say I go from being at 20 atmospheres, which is pressurized, out to 100 atmospheres, which is, woo, super high pressure. Do both sides of this equilibrium feel the pressure equally, therefore I get nothing? Or does one side experience it more than the other? Which side wins or loses?
The hydrogen feels it more
Why?
because there's 3 moles of it.
And that means
It's yeah, that cube.
this pressure gets cubed. This has the biggest effect, okay? So when you change pressure, you've got to write out the balanced equation. You write out the balanced equation will lead you to this equilibrium expression. And the expression tells us, ooh, change in pressure here is not felt evenly across all molecules. This one feels it more. So the change in pressure is experienced greater. Okay. What do you think that does to the overall equilibrium position? If I increase the pressure of this particular reaction, where I go from 4 gas moles to 2 gas moles, it pushes this way. More pressure being felt here pushes to relieve the pressure. Okay. Whenever you have an imbalance in gas molecules on the left and the right, pressurizing the container pushes towards the side with the least number of gas molecules. So in this particular case, there are less gas molecules on the right than there are on the left. So this one pushes to the right. If I did N2O4, which is a gas, is in equilibrium with two NO2s, which is a gas, and I increase the pressure, what would happen to the equilibrium concentrations? What's going to happen? I have one gas molecule on the left. I have two gas molecules on the right. The equilibrium position shifts, because this will be experiencing the pressure more, and the equilibrium will shift to the left to compensate for that. So every time you try to do something to a process that is in equilibrium, that equilibrium fights back. We see this in biology also. Your hormone systems are in a delicate balance. And we see things like men, foolish men, taking testosterone to build muscle, because testosterone is a steroid that signals for muscle growth. And they take testosterone, but that's a male sex hormone. And now your body that has been in equilibrium says, wait a minute, I have too much male hormone flushing around in my blood. So your body does what? You have too much male hormone. Makes more female hormone to balance that out. And so you have these muscle builders having all sorts of unfortunate side effects based on that their hormone system is completely out of balance. Okay, concentration, pressure. What about temperature? We already should know what the answer to temperature is. Because we did a chapter on kinetics. And we saw that the rate constants can change. The rate constant is constant, but the rate of a reaction might depend on concentration. Might depends on a case-by-case basis. Are you first order, second order, or zero order, depending on the molecularity in your elementary steps. But temperature actually changed the rate constants. And the equilibrium constants is the value of the rate constant forward divided by the rate constant of the reverse reaction. So K is also susceptible to change in temperature. That's why whenever we quote a value of the of the equilibrium constant, we're supposed to quote a temperature, because the constant is only valid over a particular range of temperatures. Now there's something additional here, and we hinted at it a week ago. Oh, look at that. Now, when we write a reaction in equilibrium, we do have to consider, because equilibrium tells us what's going on from left to right, but inherent in that, because the reciprocal of K tells us what's going from right to left. So both pieces of information that I'm going to write down are already in this data. So exothermic reactions, we can consider this way. What happens in an exothermic reaction? The heat goes where? Does it go in or come out? Okay. So in an exothermic reaction, we say reactants go to products plus heat. Heat is now a product. Write it on the side where it belongs. So heat is a product. Endothermic reactions heat plus the reactant goes to product. So heat is a reactant. And then you go back, all the way back to the original thing that you wrote down about the LeChatelier's principle. When an external force disrupts an equilibrium process, the equilibrium changes to re-establish its original position. So, I have a reaction, and it's exothermic. I heat the reaction up. What happens to my reaction? It doesn't work so well. Exothermic reactions have heat as a product. If you heat them up, they now have too many products, and you start turning your products back into reactants. This is a bonehead move. Guess what you do to exothermic reactions? You cool them down. You cool the reaction flask down and let the heat escape. If you let the heat escape, you continue to make product all the time. Endothermic reactions take heat in. Heat is a reactant. Therefore, heat these ones up. If you heat an endothermic reaction, it makes product for you. If you heat and exothermic reaction, it backfires. That's counterproductive. And it just turns out, I wrote that one up on the board by accident. Let's look at this. Depends on which way it is. Forward reaction, endothermic. So that reaction right there. N2O4. Makes 2 NO2. The delta H for that reaction is plus 58 kilojoules. Is that an endothermic reaction or an exothermic reaction? That's endothermic. Exothermic reactions have negative values of enthalpy. Okay. So put everything that we know up to this point into this reaction. Do I pressurize it? No. If I pressurize it, pressurizing a gas reaction favors the side with the least number of gas molecules, which would be my reactant side. So I'm not going to pressurize this reaction. Do I heat it up?
Yes.
Yes, I do, because this reaction is endothermic, which means heat can be considered a reactant. So it's actually on the board. If you pressurize it, you push the equilibrium to the left. If you increase the temperature, you push the equilibrium to the left, to the right. To the right. So pressure pushes this reaction to the left, heat pushes it to the right. And there are labs experiments that you can do on this because it is in equilibrium. You can take, I've seen this done, little glass bulbs, and it contains N2O4 and NO2 in equilibrium. And N2O4 has a very slight yellow tinge to it, but NO2 is orange. And if you pick up the glass ball and hold it in your hand, the gas inside goes orange. And when you put it down on the desk, it goes back to being almost colorless. Because heat is pushing, just enough heat from your hand. Heat is pushing that reaction forward. Okay, something we didn't talk about in chapter 14, but it was there right at the very, very end. It's a catalyst. Anybody know what the definition of a catalyst is? What a catalyst is something that speeds up the rate of reaction, but is not itself consumed by that reaction. And catalysts can be either heterogeneous, we see lots of metal surfaces and clay surfaces, ceramic surfaces, metal surfaces be catalysts for reactions to occur on. or they could be homogeneous. Acid is a big catalyst for many biological and organic reactions. It pops in at the first step, causes a bond to become susceptible to breaking, and then a whole cascade of actions happen, and then the acid pops off on the last step as if nothing had happened. So the acid is in there, and it's vital for the reaction to be working, but it doesn't get consumed. And the metal surface where the two material reactants meet and touch doesn't get consumed, but the reaction cannot occur without it. All right, if we remember this, I plot energy versus time. This is activation energy again. We saw that a little while ago. If my reactant is here and my product is there, then I have two quantities on this graph. That one right there is the activation energy. And then this one here is the enthalpy change. And the enthalpy change is the energy difference between reactant and product. And if that energy is given out because products are lower in energy than reactants, then that reaction is exothermic. If you flip it around, then it's endothermic. And of course, in an equilibrium process, your products and your reactants can go backwards and back and forth right here. So in the reverse way, all of this hump is the activation energy. And it's still only the gap between the reactant and the product that is enthalpy. What a catalyst does is it shaves a little bit off the top of the activation energy. It makes the activation energy lower, puts a little dimple in it, because we get now an additional step. We get a place where the reactants can coalesce at a place. We get an activated transition step, transition state right in here. So instead of being all the way up to there, I get this lowering. Does that make the reaction from left to right go better? Yes. Does it make the reaction from right to left go better? Is it now easier for product to turn back into reactants? Yeah. It's easier for reactants to turn into product, and easier for product to turn back into reactant. What have they achieved? Nothing at all. The reactions might go faster, but your equilibrium position is unchanged. Catalysts tend to make the reactions go faster, but they're not going to change equilibrium position. Okay, let's do a couple of scenarios where the concentration of reactants and products in the flask are not at equilibrium, they're at some other state, and see if we can recognize, am I going to be moving to the right to make more product to establish this equilibrium, or am I going to move to the left, siphon out of the product and back into the reactants to make product? reaction, A plus B goes to C plus D, at equilibrium. K is the value of the products multiplied by each other, raised to their powers, if need be, if they exist, divided by the concentration of the reactants. Okay. At equilibrium, when the equilibrium is established, the value of K equals the equilibrium concentrations at all other concentrations. We're going to use a value called Q. Q is the reaction quotient and describes concentrations of reactant and product not at equilibrium. At every concentration that you can conceive of other than the specific case when everything has calmed down and the forward reaction rate and the reverse reaction rate have equalized each other. This is called reaction quotient. Okay. All right, we have 3 scenarios. So we're going to calculate values of Q. And when Q is equal to the value of K, then Q is K, and you're at equilibrium. But that can only happen one time. The value of Q can be many, many, many different numbers. Only one possible permutation when Q is ever going to be exactly equal to K. Other times, Q is going to be larger than K. And when Q is larger than K, that is because Q, I'm going to write this symbolically, product concentrations are bigger than the reactant concentrations. The top part of my ratio, my quotient just means number divided by another number, just means fraction. So when Q is big, that's because it's top heavy. That means too many products. Now, if I have too many products, which way is my equilibrium going to shift to reach true equilibrium? It's going to shift to the left. So my equilibrium position shifts left. Okay. When Q is less than K, that's because C and D are not big enough. And A and B are too big. And you can either tell me that that is that I have too few products or I have too many reactants. Okay, and so my equilibrium position will shift and it will go to the right, and it will continue shifting to the right, to the right, to the right, until it gets here. And when it gets to be K, then it stops. Okay, let's do one or two practical applications of that math. And these questions are not normally more difficult than, here's a bunch of calculations, put them into your equation. Is it bigger or smaller than the quoted value of K that's in the question? That's usually everything. That's usually all that there is to this. Okay, so I've got a reaction that says 2NO, that's a gas, plus Cl2, that's a gas, makes 2NOCl, that's a gas, and that the K, by concentration, of this reaction is 6.5 times 10 to the 4, no units, at 35 degrees Celsius. The temperature is never going to appear in this calculation, but we have to quote a temperature every time we quote a equilibrium constant. Okay, this particular question is kind because it gives you mole amounts. It's close enough. I mean, at least it doesn't give us grams. Grams we'd have to convert into moles. So here's the question. In a 2-liter flask, I have 0.02 moles of NO, 0.0083 moles of chlorine, and 6.8 moles of NOCl. Are mixed together. So these are what we would call initial concentrations. These are not equilibrium concentrations. It doesn't say a reaction was allowed to come to equilibrium. The concentrations in the flask are. It said in a flask, these amounts were mixed together. In order to reach equilibrium, will the reaction shift left or right? Okay. So I've got a chemical equation right there. I can write an equilibrium constant expression for that equation. Concentration of the products divided by the concentration of the reactants. What goes on the top?
NOCl squared.
Yeah. I have 2 NOCLs, so it goes raised to the power of 2, and then on the bottom,
NO squared.
I have an NO. That gets squared because there are 2 of them, and then just the Cl. Okay? Put the numbers in the boxes. Maybe. the numbers in the boxes. What are my numbers? So the question tells me so I have this is equilibrium right here. At equilibrium, all of that equals 6.5 times 10 to the 4. Okay. I don't have equilibrium concentrations. These are what I would call initial concentrations. Let's make a little table of our initial concentrations. How much NO do I have? Nitrogen monoxide. To the question. 0.02. So what do I write here? Okay, and what are my units? Do moles go in this equation? It's concentration. What are my units for concentration?
Molarity.
Molarity. And how do I convert moles into molarity? Molarity is the number of moles per liter. So how many liters do I have? 2. Yeah. The vessel is 2 liters, and you've got a gas in it. And gases occupy the vessel completely. So this is now 0.02 moles divided by 2 liters. Oh, that's a different number. That's not the number straight out of the question. Moles per liter. And the same thing for the Cl. Now there's already a small number of nitrogen monoxide gas molecules in the container, but Dalton tells us that the gases avoid each other and act completely independently in a mixture. So we don't have to worry about any of that. So this gets 0.00415. I've now got a fictional amount of precision in my data. Moles per liter. And then the NaCl is a much bigger number than the others. So if I were to go out on a limb, I think I might know where this is going. Okay? Let's find the value of Q. Q is set up the same way as K, but it's just at every number other than the equilibrium constant. So Q is our NaCl squared. There's only one Cl in that. And O squared Cl. Okay? Which is 3.4 squared divided by 0.02 squared times 4, 1, 5. No, I wrote 2. That's a 1. I turned the 2 into a 1. That's a 1. Okay. Figure that out. This number on the top is going to end up being larger than 10. And then that's a small number, it's less than 1. And so when you square it, it gets even smaller. And then when you divide a big number by a small number, then the big number gets bigger. So I'm going to have a fairly large number at this end. The number turns out to be
2.79 times 10 to the 7.
Yeah, that's not just a fairly big number. That's a big number. Question is it bigger than K? Yep. So my value of Q is larger than the value of K. And what does that mean for this particular reaction? The question being, will the reaction shift to the left or to the right in order to reach equilibrium? Q is bigger than K.
Shifts left.
A large value of Q means this number is top heavy, and the top is product. It means I have too many products. So this reaction shifts to the left. Okay, that reaction shifts left in order to reach equilibrium, and will continue to draw out of the product box and push molecules back into the reactant box until Q goes down like a factor of 1,000 to get to this number. And when Q equals K, it stops. All right, I'll be good. Let's take a break. We'll reconvene at 10:30. Do you want that much time? We can do it earlier. I mean, the earlier you start, the earlier you get out. Or do you want to take a break, clear your thoughts, walk around the building, find a corner to scream in? Okay, 10:30. I gotta go print them. I haven't printed the exam yet. Of course, if I ever brought the exam, that's a different question altogether. I think I brought it. I'm sure I brought it.